A relation from a set A to another set B is a subset of A cross B. Okay, so it's a subset. So we can do all kind of subset operations on this, right? We saw this example. We can take the union of relations. We can take intersections, set differences, the complement, and anything you can do with the set, you can do this with one or more relation, right? So here was an application thing that we studied last time. That if I have R as a relation, ordered pairs of students and courses that the student needs to, the student has already passed, or students and courses where the student needs that to graduate, what would be the meaning of the union of R and S and the intersection of R of S and R minus S and S minus R? We saw an application of how a registrar office or a course coordination system would be interested in such question. Okay, so today we're going to begin with composing relation. Just like we did composition of functions, binary relations can be composed, right? Binary relation can be composed, a relation that has two domains. So a mouthful of definitions, but no big deal. I'm going to give you a graphical description of this thing. So suppose I have a relation R from A to B and another relation S from B to C. Okay, so these are ordered pairs where the first coordinate comes from B, the second coordinate comes from C. These are ordered pairs of S, and R is a relation with the of ordered pair, subset of ordered pairs where the first coordinate comes from the set A and the second coordinate comes from the set B. Right. So the composition of R and S, called the composite relation of R and S, the order is important here. It will be a relation from A to C. Right, these three domains involved. This will be a relation from A to C, and so this will be the set of ordered pairs where the first coordinate will come from the set A and the second coordinate comes from the set C. Okay, which two will come? So whenever I see A-B relation pair in R, and the same B appear with C, B-C pair in S, then I will write AC there. Okay, so this is a shorthand way of doing it. It's denoted by R composed with S, or R circle S, R composed with S. R composed with S will be a relation of this type. Whenever I see AB in R, in BC in R, so then AC will be in R composed with S. Okay, so it's essentially R composed with S relates elements of A, the set A, with elements of the set C through if they have a common relative in R and S. Yes?
So you denoted by R composition S.
R composed, yes.
B, C belongs to S.
Oh yes, this should be B, C and R. Yes, good, thank you. So somebody please note it down, so I will make the correction. Okay. So BC is in R. Thank you. Okay, so this is clear now. This thing is clear. So I look for AB in BC. This B is actually the bonding thing, right? It's this relates the two, compose the two relation. So whenever I see this, I directly connect relate A to C. That will be R circle S, right? So here is a thing, this can be done with any relation, any binary relation on the same set or two different sets. So here is a relation, two relations R and S on the set A. The set A has four elements, 1, 2, 3, 4, and we're going to find R composed with S, right? So R composed with S will contain, so 1 is related to 4. Now I have to see what 4 is related to. So if 4 was related to 19, I will put 119 here, right? So 1 is related to 4, 4 is not related to anything here, right? This is a relation, is an ordered pair, okay? So yeah.
The order matters?
Yes, order, it's ordered pairs, right? So 4 related to 3 means 4, 3. 3 related to 4 is 3, 4.
So that would be
yeah, so relation is a subset of ordered pairs. Okay, so 2 is related to 3. What is 3 related to here? 3 is related to 4. So that's why 2, 4 will be there. You see that 3 here is serving that B in the above definition. A is 2 and C is 4. Okay. Other examples will make it even clear. Similarly, 3 is not related to anything else, so that will be odd. That will be all. 3 is related to 2. What is 2 related to here? 2 is related to 3. 2, 3 is there, and 2, 4 is there. So there will be 3, 2 here, and 3, 3 here. No, sorry, 3, 3 here because of this, and 3, 4 because of that. Okay? Make sense? Now here 4 is related to 1. What is 1 related to by S? 1, 2, 1, 3 and 1, 4. So I will have 4, 1, 4, 2, 4, 3 and 4, 4 in the composed relation. Make sense? Okay. So generally speaking, just if you look at it, this R actually relates a number with 5 minus that number. So it relates X with 5 minus X, right? Let's check that thing. And S relates every element to so now this is it relates a number to all numbers bigger than itself, right? That's S. And so if I combine them, this is what basically I'm going to get, right? A is related to B if B is equal to A minus 5, and then if B minus 5 is bigger than some other number, that will be there, right? So this is not very important. This is the application of definition. This, yes. That's just because you see, I look at this, what is 1 related to? If I want to put it in word, I want to see how this, what does this relation actually represent, right? Not important for you, forget about this one, okay? But this is because it came from database example, and this is how, these are just toy relations, but in database, we have to make these kind of relation, and this has meaning that solves my problem, and so, okay. So that's not just very specific to this thing. Here is another example. A is the same set 1, 2, 3, 4. I have 3 relations R1, R2 and R3, right? And all 3 of them are pairs of A cross A, right? These are ordered pairs where the first coordinate comes from A and the second coordinate also comes from A, right? So binary relations. Let's compose R1 with R2. Okay. So R1 relates 1 to 1. Right, and R2 relates 1 to 1. So this one is actually the different, that's the A. The second one here and the first one here is actually the B, the common thing, and the third one here, this one, the second one in the R2 is actually the C thing. So I will relate 1 with 1, that is the 1, and this is the AC thing, right? Also 1 is related to 2 here, right? 2 is not related to anything here. So I will not put anything else. Okay, 2 is related to 2 here in R1, but that 2, the second 2 is actually not related to anything in R2. So this not going to give you, not going to be composed with anything, right? Here 2 is related to 1, and the 1 is related to 1. So this 2 is this 2 1 is there because 2 is related to 1 in R1, and the 1 is then in turn related to another 1 in R2. So that's why I put 2 1 there. Okay. With these examples, it should be clear. 3 is related to 3, but R2 doesn't relate 3 to anything, so I won't put anything there. Yes.
Sir, in the R1 you want to compose R2, why is there 2 1?
So good. That's a good question. So 2 1 is there. So in R1, 2 is related to 1. So is 2 related to 1 in R1? So let's let A be equal to 2 and B equal to 1, right? So the definition said that whenever I see AB in R1, this will be the definition. Whenever I see AB in R1 and BC in R2, then I should just make another ordered pair in R1 composed with RC. That will be this A and this C. AC should be in R1 composed with R2, right? So that's now plug in A equals 2 and B equals 1 and C equals 1, you get that thing, right? So this is 2 1, 2 1 and 1 1. So that's why I should put 2 and 1 here. Did guy stole something? So 2 1 and 1 2, yes, whatever, right? Clear? Okay, let's do the other examples and it will make more things more clear. R1 composed with R3. Okay, R3. So in R1, 1 is related to 1, right? Now whatever, look, think of this second one as a distinct thing, like a blue one. So whenever I see this blue one now, whatever follows it should be added with the first A, right? So R1 relates 1 to 1, R3 relates 1 to 3. So I should put 1 3 here in R1 composed with R3. Okay, R1 relates 1 to 2. Whatever 2 is related to in by R3, I should put that thing, right? So R2, R1 2 and 2 1. So there should be 1 1 here. Okay, you have to do all pairs. Okay, how many ordered pairs are here? 5 ordered pairs. And how many ordered pairs are here? 3. So I should check this 5 times 3 pairing and try to see this pattern, right? If whenever some A in the R1, the first coordinate of R1 is indirectly related to some C in the set C or the second coordinate of S, then I should, if they have a common friends, right, a common following friend and whatever predecessor, if they have a common successor and a common predecessor, first coordinate, second coordinate, then I should add that thing. Okay, pictorially hopefully it will make more sense. So you can complete the rest of them in these also. Okay, do these examples. So these are in your ICPs. Let's just do R2s composed with R1s because I want to make a point based on this, and then we will go further. Okay, what will be R2 composed with R1? So R2 relates 1 with 1. So whoever 1 is related to in R1, that will give us an ordered pair for R2 composed with R1. So 1 is related to R1, 1 is related to 1 in R2. What will I get here? 1 1. So 1 1 will be there. 1 2. So I should get 1 2 here, and that's it, right? So 1 1 and 1 2, right? Is it different than R2 composed with R1? R2 composed with R1 is the same as R1 composed with R2? No. Right? So one is 1 1 and 2 1, and the other is 1 1 and 1 2. Right? These are different ordered pairs. Okay? 1 1 is the same, but okay. So generally speaking, R1 composed with R2 is not necessarily the same as R2 composed with R1. Right? It's not commutative. Okay, and to do the rest of them, R1, R3 composed with R1, if you do it, you may see significant differences between the two. Okay, so here is a more pictorial way of doing it, and how to find something. This is not really important anymore now. For everything, you have a Python script, you have a database. You just do one click, and it'll give you whatever you want, right? So this algorithmic way of doing mathematics, learning the algorithms, learning the methodology of doing something is not really important. What's important is the definition and its applications, right? So you are able to model your problems with that, and you can use that to solve your. This girl, can you stop using phone? So this is a good way of doing it. So what happens is, so R is a binary relation. We can represent a binary relation with this bipartite graph, right? It's a relation from A to B. So I should write A on one side, B on the other side, and if X is related to Y, I should put an arrow between a line, directed line from the element of A to the element of B, right? So think of this as R, that is the relation. A is related to 2, B is related to 1, B is related to 4, C is related to 3 of them, and D is related to 1. Okay? So make this. The other relation S is from B to C, right? This B has to be common. The set B domains of the second domain of R has to be the same as the second domain of the first domain of S, right? Because we are looking for common thing there, common relative. So you write R on one side, the bipartite graph. You write S on the other side is a bipartite graph, right? Now notice this B is the same as this set, right? So I can just overlap them on each other, right? I can write it like this. So this is a concise representation of both relations simultaneously, right? This is the relation R, these lines, and these segments are relations, the relation S. Okay? Okay. Now, what does the thing say? Now look at the definition. If AB is in R, and BC is in S. That means if there is a line from some A to some number here, that is, let's say, the B. Now whoever B is related to, A should be directly related to, right? So then you shortcut them. You shortcut the indirect relation, the indirect path from some element of A to some element of B, some element of C. You make it as a direct path, right? Make sense? Look at this. A is related to 2 and 2 in turn is related to Z. So in the composed relation, A would be related to Z. Okay? Here A is not related to anything else. B is related to 1 and 1 is related to X. So there should be a direct relation between B and X. Okay? B is related to 1 and 1 is not related to anything else. B is related to 3, 3 is not related to anything else, so I don't have to do anything. C is related to 1. You can go from C to X, right? In this graph, you can go from C to X, right? From C to 1 and 1 to X. So you put a line from C to X, you directly relate C to X. And similarly, C is related to 2 and 2 is related to X. So you put CX. Now it's a set. CX, you can write 2 twice or thrice, it's still one thing, right? So C is related to it. C is related to 2 and 2 is related to Z. So now in the composed relation, C would be related to Z. Okay, here C is related to 5, but 5 isn't related to anything. So through 5, C doesn't get related to anything, right? So these are the intermediary, the B's, this domain B, the second domain of R and the first domain of S that serve as the intermediary between elements of A and elements of C. Make sense? That's the composition of relation, just like we did. Now, if we can compose a relation with, if we can compose two relations, then we can compose the relation with the self also, right? R composed with R, that will be another relation, right? So indirect relation, but the same elements and the same thing. So if I have a binary relation R and I can compute the R composed with R, we denote it typically by R squared, right? So R second. This will be just plug in, just substitute the for S, substitute R. Right? So if AB is in R and BC is in R, then AC should also be in R squared. AC should be in R squared. Exactly the same definition, except for S is now replaced with R. Okay? So you can compose a relation with another relation to get yet another relation, right? R composed with S is also a relation. It's also a subset of ordered pairs of some different sets, maybe A cross C in this sense. Set. So then you can compose R with R squared. You can compose R with R cubed. You can compose R squared and R to the 4, right? You can just do this kind of iterative composition of a relation with itself. Okay? So generally speaking, R to the n is the relation R composed with itself n times, right? It's written as R to the n. It is equal to, if n is 1, then it's just R. If n is 2 or 3 or 4, bigger than 1, then we say it's R composed with R to the n minus 1 or R minus 1 composed with R. Okay? Happy? Yeah, okay. So this is slightly, I pronounce it differently, not the same, but this is equal. You can write that this is equal to R composed with R to the n minus 1. Okay? Relations composition is associative. It's not commutative, but it is associative. Okay, so you can do the in any order of the operations. Okay, so this is some of them. We may have done it earlier. It's the same R1 and R2. So, but this is composition of R's relations with themselves. Go home and do them. Okay, no big deal. It's the same thing. Just apply. If it's too many things, then I mean, if it's a few elements, 3, 4, 5, then make it draw the diagrams, right? But make sure that you process all. How many pairs of ordered pairs are you going to process? How many pairs of ordered pairs are you going to process, or ordered pairs of ordered pairs? How many? Just tell me in this case. How many pairs of pairs you need to process to find out R1 cross composed with R2, or if you are finding R1 composed with R2, you have to process 15, right? But if you are computing R1 composed with R1, then how many you have to process? 25, right? So you have to see all pairs. Okay, R2 composed with R2, you have to process 3 times 3, all pairwise. Okay, and that's, you can draw that thing and you will see that there will be these kind of possibilities. So look at this diagram. How many pairs of elements in A and how many ordered pairs can be made by A cross C? How many ordered pairs in A cross C total? The cardinality of A times the cardinality of C. Some of them will be in the relation R1, R composed with S, right? You have to check which one, right? And that shortcutting method is also easy. Let's just think about it so that you understand. Let's say AB is a relation where A is a parent of B. It's a relation on the set of people. A is a parent of B. What will be R squared? So, what is the relation of R composed with R? What is the relation R composed with R? The definition would say if A is related to B and B is related to C, then A should be related to C in the composite relation, right? So here, yes, please. A is the grandparent of C. So if A is a parent of B, and again apply R again, B is a parent of C, so then A is a grandparent of C. Yes? So this is R squared. In this case, what will be R cubed? The great, what did I say, grandparent? So great grandparent, right? And great great grandparent. Okay? So this is for your homework. Go home and do this. Relations composition of relation is associative. Okay? You can do them in any order. The composition you can do in any order.
So
Yes.
why n minus 1?
What?
1 of the n minus 1.
Yeah, so it's Rn is equal to Rn minus 1 composed with R.
What is n minus 1?
So R composed with itself n minus 1 times. Yes.
इसको प्रूव करने के लिए n की कोई वैल्यू हम इनपुट करेंगे?
No, for any n, this is true. Proof करने के लिए you just need the definition. So to begin with proof, this is no n here. This is no n. This is just 3 relations, right? It's composition of different relations, and this will just is just a corollary of this thing, right? If A cross B, A is composed with B composed with C is the same as A composed with B composed with C, so then it's just plugging in the different values. Okay.
Sir,
Yes. Just definition, plain definition of composition. Yes.
commutative तो नहीं होती ना?
No, not generally. In some cases they may be. I mean, so if it's an empty relation, empty set, the relation, then it's commutative. Okay. This is more, again, the purpose of this thing is just to give you some terminology so you don't get scared of them, right? Some very basic concepts of this thing. This is a whole part of so this partial order set, the post set, there are books written on post sets. There are a lot of stuff, a lot of work here. Okay, in combinatorics and discrete maths and graph theory, a lot of people work on this thing, and so I just wanted to there is a whole theory of the first 2 things, the first 3, and also the 4th one is like a whole database courses, right? So you can do at least 1 or 2 courses. Typically, people do in a BS program, and then there are PhDs after PhDs and a lot of work on this type of databases, right? These relational databases. So a relation from x to y is a subset of x cross y. This is what you really need to remember, and everything will follow from this. For everything we did so far is just if you know x cross y and the subset, then you know relation is a subset of x cross y. Nothing, everything is just an application of this definition. The previous homework also just needs this definition. A binary relation on a set X, right? We call it binary relation because you can have ternary relation or n-ary relation, k-ary relation. So a boundary relation on a set X is actually a set X cross Y. If both domains are the same, then we call it a relation on a set X, right? So you know n-tuple, right? N-tuple is an ordered collection of n objects. Ordered pairs is two tuples, right? Ordered collections of two objects is called ordered pairs, shorthand words, ordered triples, right? Now, generally n-tuple, we can apply a projection on n-tuples. Projection on n-tuple is basically the word in programming. They will tell you the first thing they teach you in programming is subsetting. You know that, right? Well, not the first thing, but the actual major thing they teach you is subsetting, right? So you know that, right? They teach you array, then they'll say, okay, how to get an element from 1 to 5 substring. Remember substring? It's not correctly, it's called subsetting. It's substringing, right? Subsequence. Okay. So a projection is basically, in that sense, a subsetting, right? You select a few columns of the table of a vector, a few coordinates of a vector is called projection, right? You must have seen the projection. So if I give you a 2D vector, here is a 2D vector, let's say 2.4 and 7.0, right? So this x value is 2.4 and y value is 7.0. What is the projection of this vector on the x-axis? It's 2.4, right? In algebra, this is the closest point on x-axis to this point P. This is a point P. The closest point to an x-axis is 2.4, right? Is the x coordinate of this, right? This isn't closer. This point isn't closer. This point isn't closer. That's simple Pythagoras theorem, right? The hypotenuse is always bigger than the perpendicular, right? So because here the base is 0, this is what's called projection, right? What is the projection of this vector on the y-axis? 7.0, right? And that's the closest point to this thing. You can find the projection of a vector on any vector, right? What's the projection of this vector on one time I need colored chalk is far away. What's the projection of this vector on this vector, right? So vector can be written as a point, it is a point, or it can also be written as a line from origin to this thing. What's the projection of this vector on this vector? So the question is, what's the closest point to P on this line? And that also you should, this must be, you draw a perpendicular, a normal to this vector, right? This should be normal, it should be a 90 degree angle. If you take this point as a projection, then by Pythagoras theorem, this is not the closest. This distance is bigger than this distance. If you take this point, this isn't not closer, right? This is the projection concept in database, and this is, we are doing the first type of projection, which projection only on the axes, right? On one or two or more of the axes, right? If it was a 3D point, I could find the projection of x of this point xyz on the xy plane. I can find the projection on the yz plane. I can find the projection on xz plane, right? In any plane, you can find projection on any. It's projection onto a subspace, right? Principal subspace. So this is actually that projection. I give you a vector, a projection on these coordinates, these axes I1, I2, Im is basically just keep these axes, these coordinates, and remove the rest of the coordinates. Okay. So projection keep the selected, the chosen, the given m coordinate, and remove the remaining n minus m coordinates, right? Let's do this example. Apply the projection P14 to this vector, this 5 tuple. First tell me the type of this projection. What will be, stop this thing please. Cannot use electron. What will be the output of a projection, the type of the thing, not the value of the thing. What will be the P14 projection on this A1, A2, up to A5? It will be summary. Sub-array, yeah, don't use array. Did I use the word array? No, it will be yes, lower dimensional tuple, yes. Not the value, that's the value. It will be an ordered pair because I am selecting a pair of coordinates and discarding the remaining 3 coordinates. So it will be an ordered pair, right? It will be an ordered pair. What ordered pair will be here for this and 5 tuple? It will be A1 and A4. The value at the first coordinate and the value at the fourth coordinate will be, it's a projection of this 5 tuple onto this two axes, right? These 2 coordinates. Okay, so this is what we are going to get. Okay, so projecting on the first coordinate and the fourth coordinate. Just when you told me here, what's the projection of this vector on the first coordinate? The x coordinate is 2.4, right? What's the projection on the second coordinate? What's the projection on the first and the second coordinate, or the whole xy plane? It's exactly the same point, right? What? Yes? You didn't get what? Okay, so you know projection for vectors, right? The projection of a vector, this is a vector, 2-dimensional vector in xy plane. This is the x value, the horizontal displacement, and this is 7 is the vertical displacement, right? I asked what is the projection of this vector p on the x-axis, right? So I just defined the word projection in the geometric setting. Projection on some axis on a vector is the closest point on that vector, on that line, to the given point. Okay, so the x-axis projection will be 2.4. So in more algorithmically, we say keep 2.4 and discard the rest of the coordinates. The projection on the y-axis will be keep the y displacement and discard all other displacement. That same concept is here. Projection of a vector over n-tuple is actually on 2 coordinates will be a 2-tuple, it's an ordered pair, and this will be just select those values. And so look at this, I have a 4-tuple here, and I want you to apply the P23 projection onto this 4-tuple. What will be P23? Not the value, what will it do? It will keep the second coordinate and the third coordinate value and discard the remaining coordinates, right? So it will be projection onto this subspace. This will be this 4, 1, 2, 3, 4 and CS, right? It will discard the second coordinate and the first coordinate and the fourth coordinate. It's clear? So big word, nothing there. Okay, there is just no meaning there. It's a simple, very simple concept, right? But you please understand what's written there. For technical completeness and correctness, I wrote this thing. That this is a projection P I1, I2, I3. These are the indices of the coordinates you want to keep, right? You keep those coordinates and remove. So there are some basic thing. M has to be less than or equal to n. What if m is bigger than n plus 3? You are basically saying out of these n dimensions, keep n plus 3 dimension and discard the rest. It just doesn't make sense, right? This is a compile time error in this statement, right? Yes? What does it say if I say if m is negative 17? What would that be? It's not a statement, right? Keep the negative 17 coordinates and discard the remaining. There is nothing called negative 17 coordinates, right? Okay. Now, if you want to apply projection, we applied projection to one tuple, right? One ordered, one n-tuple, one k-tuple or whatever the thing is. We can apply it to multiple simultaneously, right? And that would just be keeping, think of the relation is a table, right? And then it will be just selecting, keeping a few columns and discarding the remaining columns. Okay. So if we apply a projection P234 to this relation, this is the relation. It's a subset. It's a set of ordered 4 tuples, right? We applied to one 4 tuple. We applied this projection to this 4 tuple, but now it's a collection of many 4 tuples. Yes, please. Sorry. This is your choice. As long as you're clear with the language, you have to be careful with it, but it's generally choice. Typically, I start with the 1 Generally we start because it's easier to talk about, right? Sometime I will show in a minute, you will see that sometime we will start with 0 also, but you have to be clearly mention that. Okay, apply the projection P234 to this table, to this relation. It corresponds to just keeping the second, the third and the fourth columns and discarding all other columns, namely the first column, right? So this relation, this projection will give us this, I don't know what if you call it, subtables or something. Make sense? Now there is one slight tricky part here that you have to keep in mind. Projection is, that's it, we don't need anything else, right? Just one quick more thing. How many of you have heard the word projection in database or database system, or in what sense did you write?
When we write queries, we tell them what.
Yeah, this is when we say select name and age and GPA where age is less than or equal to 14, that is basically projection on the thing, right? On these 3-4 columns, right? Just select these 3 values where if it matches some criteria. So that's actually query. This is query, right? So we are writing queries. So the where is what we covered. What comes after where is a logical condition, is a predicate that we studied in detail earlier, right? Now it's a select X bar, select star or select others part of it. Okay, so let's don't worry about that if you don't know databases or queries or SQL or something. That is not very important. Okay, so apply the projection P234 to this relation. You keep the second column, the third column and the fourth column. Why? Because it says 2, 3, 4, keep these indices and remove the rest of the coordinates, right? So apply the projection P23 to this relation. What would that correspond to? Keep the ID and the department columns and remove the name and CGPA columns, right? So this is what we will get. Okay. One quick thing. So sometime, this is just one last thing that you should have come up with yourself. A projection on a relation, if you apply a projection on a relation, you get another relation, right? Sometime a lower dimensional relation with the lower degrees, right? Fewer domains, fewer columns. So you will get that, but it's still a relation. It's a set, right? A set meaning repetitions don't matter. Sets meaning order doesn't matter, right? You can write this order doesn't matter, mean you can write this row at this here and the second row at the fourth place. That is not important. Right? This order is important. You can't write GPA in a major in a ID column and ID in a GPA column and so on. Right? That order is important. So sometime it may, so apply the projection 1, 3 to this relation. It will be to keep the name column and the department columns. Right? Keep these 2 columns and discard the rest of the fields. This is what you get. But if you look at this, if you think of this, this is a relation, this is a set. Look at this set is actually equal to this set, right? Because Ahmad in CS is the same as Ahmad in CS, right? You can write it 19 million times, it's still going to be one Ahmad in CS is an element and Ahmad in EE is not an element, right? That's what we know, that's the set, right? So is this clear that this is actually this relation? So sometime a projection may reduce the number of the size of the relation. Yes, please. Yeah, it's a set. It's a set of ordered pairs or ordered triples or ordered k tuples. If you select k out, if you project an n-tuple onto a k space, a k dimensional subspace, you will get k coordinates, right? Those k coordinates, if these 2 vectors are exactly the same, you have the set of k dimensional vectors or k tuples. If they are repeating, then they don't matter.
So this is why we have primary key.
This is why you have primary key and foreign key, the concept of it, right? You generally want to keep the primary key in your queries, in your projection, because the moment your primary key is this unique key identifying a record. And n-tuple, a k tuple, right? So if you lose If you lose those things, if you don't have a k-tuple, if you don't have primary key included on the projected space, in the projection space, you will lose some record, right? So the question that had just exactly that was the answer that you need to give them. In what scenarios we may get fewer records? That's when there are two or more records or two or more order n tuples whose selected coordinates are exactly the same, right? In that case, you will lose them. And in what case, what coordinate should be or would be can be included, that will make sure that we don't lose any data. Yeah, the primary key. In this case, ID, generally speaking, the primary key, and that's the whole concept of a primary key. If I was teaching database, this is where we will start this is how I will teach primary key. Yes?
When we have relation between we have a two-order tuple, so we say it's a relation from A to B.
Two order tuples? Ordered pairs, yes?
So it's a relation from R to S, etc. But if
No, that R and S were two relations. It will be relation from the first column to the second column, yes?
But if we have multiple columns, then how do we define that relation?
It's a subset of A cross B cross C. You don't say it's from A to B and C together or from AB to C. That's not what it is. You say it's a relation from.
So basically सेट्स होने की वजह से वो यूज हो जाता है. बट इफ अगर हम उसको किसी तरह डबल्स के अंदर ले जाए तो हम ये कर सकते हैं जैसे प्रोजेक्शन ऑफ और उसके अंदर भी प्रोजेक्शन डाल दें ताकि लाइक वो सारा ऑर्डर टपल्स के अंदर आ जाए.
सॉरी दोबारा बताओ.
जैसे फर्स्ट करेंगे लाइक हम लोग प्रोजेक्शन ऑफ और प्रोजेक्शन कर लें ताकि वो हमारे लाइक वो यूज ना हो सके डेटा. ये कर सकते हैं.
No, projection of a projection कैसे होगा? That's like you select the out of 10 for all columns, you select 5, and then out of them you select 3. How would it make sure?
रोज को सिलेक्ट कर सकते हैं rather than कॉलम्स. लाइक प्रोजेक्शन में हमारे कॉलम्स सिलेक्ट होते हैं.
The projection actually rows को ही return करती है, but select columns को साथ. I don't think it makes sense. That is actually called subsetting. Queries is used for that. Queries basically says select those records where the name starts from, where the department is CS. That will be selecting a few rows. Okay? No, so records, so here is the thing. Suppose you want to talk about, so you have a whole record in Zambil, you have a lot of records, right? A lot of stuff. I want to say, I need the students' grades in the Physics 101. So I would say, project the Zambil data onto name or ID and Physics 101 grades, right? So I don't want to see the whole thing. I just want to make my to analyze how people are doing with CS in Physics 101 and who is taking it, who is not taking it, that kind of. Okay, so projection is an extremely important thing when you have to do this kind of subset. Databases typically are really huge, so you have to do this. Next important thing is actually if you know these two words, projection and join, and the concept of primary key and relations, right? The general thing. You are done with 30%, 25% of the database course. Okay, the concepts in database. There are many techniques to do this. There are many algorithms to do this thing. So join is the most important concept in databases. Okay, outer join, inner join, or whatever called X join, or a lot of other nonsense. They do this here. No meat. This is actually all the theory. Okay, join is a little tricky. Okay, it's a little tricky. You have two relations. One is of degree m, the other is of degree n. Right? See the color coding here. Okay, there is a red relation R. There is a blue relation S. The red one R has degree m, meaning it has m columns. If you think of it as a table, S has n columns. If you think of it as a table, right? It's degree n. Now, the join of them. So join depends on what are you joining on. That's an important thing. What are you joining on, right? So we are restricting ourselves to joining on. There is a number is a parameter of this thing. So you basically compute. Okay. So let me just please pay attention to this thing. Okay. So you have a relation R whose degree is m. What does it mean? Every element in R is a m-tuple, right? It has m coordinates. You have S, which is n degree relation, degree n relation, right? So it's a table which has n columns. This one has m columns, right? What will be R cross S? I told you these are just sets. You can do all kind of operations on them. R union S, R intersection S. You can do R, the Cartesian product of R with S. What will this be? What is the Cartesian product of two sets? The set of all ordered pairs with the first element, the first coordinate comes from the R and the second coordinate comes from the. So this will be actually itself a relation. It will be, this will be basically whatever is written R. This is the first m tuple in R, the first element of R, and then comma the second, the first this ordered pair. These are the types of element in R cross S, right? Every row of R joined with, concatenated with, paired with every row of S. Okay, so sorry, no, every row of R. Okay, so suppose R has 15 rows. So these 15 m tuples are in R, and n has 7 rows, right? So what will be, how many elements will be there in R cross S? 15 times 7, right? That will be, that's, we know it's ordered, we know this Cartesian product, right? So join is the subset of a Cartesian product, right? With the restriction, with the parameter p, with the last p element, or you take the concatenation of all rows of SR with all rows of S, and then check where the last p coordinates of the row of R are the same as the first p coordinates of the rows of S. This is called the join. Okay. So look at this thing. It's a collection of all of those things. All of those things. This is a m plus n minus p, where the last p coordinates of R are the same as the first p coordinates of S. Okay. Again, example should make it clear. But this is, you take every m plus, this is m tuple in R and every n tuple in S, write them like this on top of each other. If the first p, last p here and the first p here are the same, you don't repeat those coordinates and write this m plus n minus p coordinates. Okay, keep this picture. I'm going to come back to this, but is this clear? It's JPRS, JP, the join, and the p is the number. Join for p number, RS is another relation which combines things like this. I'm going to give you example. Yes, please.
Same now coordinates.
फिर नहीं include करते. They are not going to go into join. Okay. No, P0 नहीं होगा, but then they will not. We will include those which match this criterion, and those which do not match fulfill the criterion will not go. Look at this example. So I have a CS, this is a practical examples the way we do, right? The way RO and room assignments and these things work. So the department comes with a course assignment. This professor is going to teach this course. Course code and name, right? That's what they do. So this is a typical department course assignment. The department chair does this, right? RO does this. RO doesn't know who is teaching what. RO knows CS210 is going to be offered, so it's going to, the scheduling thing is done by RO. They say, okay, it's going to be in this room and this day, right? Now, if I want to find my schedule, these two have the information separately. I want one consolidated thing, everybody's schedule or just my schedule, right? It will be the join of these two columns, these two relations on the course code, J1 CS. So, what will happen is, look at this thing, this is the join thing, okay. How many rows are here? How many rows are here? How many rows here? So, out of these 20 possible concatenation, I selected only these 5, okay, because out of all those 20, these 5 are such that the first coordinate, the last coordinate of the course assignment relation is the same as, the same value is the first coordinate of the schedule, the semester schedule coordinates, okay. So, look at this, Imdad DM210 will be joined with which of these rows? Imdad DM210 will be joined with the first row. Why? Because the code, the last coordinate here is the same as the first coordinate here, right. So, that is why Imdad DM210, and you know, so you got my schedule. Now, even if somebody is teaching 2 sections of a course, right. So, Junaid is teaching data structure or digital systems, this the course code is 310. Which one will this be? So, 211 is computer programming, let us say CP, and it has 2 sections. 211 has 2 sections. So, Basit CP and 211, why is it not coupled? Why is it not joined or concatenated with the first row? Because the last coordinate here is 211 and the first coordinate there is 210. They will not be, they are not the same, that is why those pairs will not be doing this, okay. Why is it not done with the third one? Because this is 211 and this is 310. I have Basit CP 211 Q02 room number Wednesday. So, this is why we get here Basit 211. These are 2 different rooms, 2 different times where Basit is going to teach CP. These are 2 different sections. Does this make sense? Yes? Yes, please.
Sir, if there was a row, this code would, in the same course schedule, the code would not be found in the course assignment.
Yes, good question. That will not match with any. So, if there was a course 511 and it is not here, then it will not be matched with anything, right. And basically it would mean that we do not know, we cannot find out, based on this information, we cannot find out that person's schedule. This makes sense? So, just let us ask yourself some basic preliminary questions about this stuff. What will be the dimensionality of JPRS? What will be this, the maximum dimensionality possible? I told you it comes from concatenation. So, if R has m dimensions and S has n dimensions, the dimensionality has to be less than m plus n, right, because I am concatenating. There are certain restrictions on those, right. So, the P, the last P here and the first P here are matching and I write it only once. So, the actual dimensionality will be m plus n, that is the concatenation, but now because I do not repeat the P of them, so it will be m plus n minus P, right. What is the maximum possible size of a join in this sense, the number of rows? What is the maximum possible coordinate? How many different m plus n minus p tuples can be there?
Whichever one has more rows.
No, the maximum, not total. What is the maximum total number of rows in such a column? And when will it happen? No, m plus n minus p, that is the number of columns. We said it will be m plus n minus p.
Always seem to have at least one common field between the 2.
No, what is the maximum possible? Yes, please.
The number of elements in column P.
It's a subset of cross product of R and S. Those ordered pairs which match certain condition, will be added into join and others will not be added into join. So, the maximum cardinality of this new relation will be the cardinality of R times the cardinality of S, right. When will it happen? Suppose all of these course code was CS100 and all of these courses were CS100. Yes. So, in that case there is just nothing there, everybody matches everybody. So, this will be 4 times 5 rows here, all 20 rows will be there, right. Most probably meaningless, but that is what it will be, right. What is the minimum cardinality? It is a relation, it is a set, minimum cardinality is 0 if it is an empty set, right. Yes, somebody, you raised hand earlier. The 1 means, that is a very good question. So, there is a P here, right. This is what are we matching, right, how many are we matching. So, this the 1 means you look at the last column here and the first column here, the last one column and the first one column in the other one, and try to match them. If it's match, you keep these 2 rows, the concatenation of these 2 rows. If there is a mismatch, you don't keep these concatenation of these 2 rows. Okay? Is it clear? Don't worry too much about it. Okay? It's just a concept. I wanted you to introduce. I wanted you to get familiar with it. You will learn it when you need it in any course or any project, and so you won't be scared of it. There's slightly more to it than what I told you. There's a little bit more concepts there. Yes, please. A 2 hota, so there will be, that's very good thing. That will be comparing code with room and this course with this code. The last 2 there, you will try to match the last 2 columns in the last 2 columns in the first table and the first 2 columns in the second table. There won't be any matching there, right, because you are comparing apples with oranges. Yeah. Yeah. So then it's just not, it's a compile time error, or it will be just say no match, right. You are asking a number is equal to a room number, they will say no, it's not, right. That's what I said. There is a little bit more to it in actual database theory. That is not really strictly not this definition. You don't say the first P and the last P, the last P and the first P, you don't say. You say some P, right, some P columns here should match some selected P columns there. Now, they don't have to be the first one or the last one or something like that. Okay. So, there we do this. So, this is what you see, join generalizes intersection and cross product. It's J0 is like, okay, don't look at any matching, just concatenate all rows here with all rows here. So, that will be the 4 times 20 thing. Jn meaning is just intersection, just match all the n coordinates and n coordinates there, right. If both are of degree n, just match them. So, essentially you are copying whichever are common, just add those rows. Okay. So, don't worry, you read this further into this, and then you don't need too much of this thing. Okay. So, J0 I will tell you, but you should just pronounce this thing. Okay, what is J0? How would you say this, write this J0 thing? J0RS. Take a row of R and a row of S. And if the last 0 columns are the same as the first 0 column here, then you write the concatenation without duplicating the column, matching column. That's what it's, how it sounds, right? JPRS is take a row of R and a row of S. If the last P columns here and the last P coordinates here and the first P coordinates here are matching, then you keep this pair of rows. Otherwise, don't, right? So, J0 is the last 0 column and the first 0 columns are matching, but 0 is essentially you are not putting any restriction on it. So, you are writing all the coordinate of R times coordinate of S. So, it's just the cross product, right? The one I told you here, this 4 times 5, 20 or something, 5 times, 17 times 5 things here. And if it is n, then you are basically matching all columns, okay? Okay, you are still allowed to go if you want to go, right? Okay, so we talked about relations, then we skipped into a few operations on relations, a combination of relations, application essentially. But that could go back to the properties of relations, okay? And based on this, we'll build two different types of relations that are widely used in computer science, okay? So we said a relation is from x to y is a subset of x cross y. We'll generally now onward talk about relations on a given set, okay? So a relation on a set A is just a subset of A cross A, okay? Same definition. Then we said a relation is reflexive if every element is related to itself. If every element of the ground set, a relation on a set, we are now going to talk about relation on a set only. A relation on a set is called reflexive if every element is related to itself. If A is part of the relation, is an element of the relation for all elements A of the ground set, okay, of the domain. And a relation is symmetric if whenever AB is there, then BA is also present in the relation, okay. And the relation is transitive if whenever AB is there and at the same time BC is there, then AC is also there. Then the shortcut direct relation is also present. Direct related pair is also present, right? You should now know something, you should be able to picture it based on what we saw for composition of relation, okay. So these three things, now based on this, we are going to define what's called equivalence relation. An equivalence relation is a relation on a set if it has these three properties. If it is reflexive and it is symmetric and it is transitive, okay. If these three properties hold, then we call it an equivalence relation. Nothing more to it. There is nothing more to it. The rest are examples and applications and just verifying if these three properties hold. That's it. Our lecture is finished with this thing if you understand this block, right? And similarly for partial order, I'm going to give you one thing. The rest are just technical mumbo jumbo for this stuff, okay? Understand this. Why do we need relations? It actually generalizes what we call equality. When things are equal, equality is a very artificial construct. It only works for numbers. Nothing else in the world is equal, right? This is just equivalence relation. It's some kind of generalized equality. Those of you, communism failed because they couldn't understand what exactly is equality, right? They tried to make people equal, right? All men are created equal. So you must have seen the US Declaration of Independence. We hold these truths as self-evident that all men are created equal. Those idiots who owned slaves, who smuggled in slaves from Africa, who grabbed the land from Mexicans and from Indians, and now they say all men are created equal and these are a self-evident truth. These idiots didn't know it is equivalence. It's actually, so equivalence relation is actually it's a general form of equality, okay. And you will see now, I'm going to give you one application that we did last year, which actually led to this all ChatGPT nonsense. Generalized equality is, so any notion of equality, equality between things have to be these properties, have to have this property. Suppose I have the equal relation on the set of integers. Can you give me a few elements of this relation? A few elements of this relation, equal relation on the set of integers? 1, 1, 2, 2, 0, 0, negative 4, negative 4. So just I was waiting for that one example there, right? So that's equality. Is it reflexive? Is it reflexive, right? 1, 1 is there, 2, 2 is there, negative 17, negative 17 is there. Is it transitive? No, it's not. So if A is equal to B, then B not equal to A, then isn't B equal to A then? Yes, please. Sorry. Yeah, we have to have all. It's an infinite size relation. The set is infinite. There are infinitely many ordered pairs there, right? So it's equal, right? It's transitive. It's symmetric. If A is equal to B, then B must be equal to A, Otherwise equality is not a thing, right? Numbers equality. And it's symmetric also. If somebody tells you I have the same number as Ahmad and Ahmad has the same number as Fatima, then I should have the same number as Fatima, right? Make sense? No? What did I say? Who was the first idiot? No, Ahmad was the second. Okay. So what's your name? Zain. Okay. So Zain has the same number as Ahmad. He substituted idiot for his name. So Zain is the same number as Ahmad. Ahmad has the same number as Fatima. Then does Zain and Fatima have the same number? They have the same number, right? So equality is transitive, right? In any notion of equality must have these three properties. Would it make sense if A is equal to B and B is not equal to A? Right? All men are created equal. All men are equal, but some are more equal. All animals are equal, but some are more equal. Know that thing? The rest of you don't know? All animals are equal, but some are more equal? No? Never read Animal Farm? Never read Animal Farm? So it wouldn't make sense if a relation is not, if inequality, a notion of equality, a definition of equality is not reflexive, right? If a number is not equal to itself, that just doesn't make any sense, right? And similarly, symmetry. If A is equal to B and B is not equal to A, then that's just doesn't make any sense, right? And the other thing, right? If Zain and Fatima has to have different number, even though both have the same number as Ahmad, that will be a big, this will be a, just doesn't make sense, okay? So any notion of this thing has to be this. So we were working, a couple of years ago, a PhD student was working on text analytics or natural language processing, NLP, which was, the problem was to find duplicates among text, from paraphrase identification. It's called paraphrase. You can say the same sentence in many different ways, right? So those days the examples was hot, and those we were working on that thing. So this was the 2016 US election, presidential election. I'm asking a few questions and see if the questions are exactly the same. Will Trump win election? That's a question, right? Will Hillary Clinton lose election? Are they the same questions? Not the same question. Why? If you are going to answer this question, if you are sitting in Microsoft help desk and somebody asks you these questions about something is wrong with my Windows, right? Now you can ask in many different ways, many different words, actually the same question. The same question in the sense that answer will be the same, right? They are going to give you the same instruction, do this, click here, click there, and recompile and restart or whatever, right? So actually anybody who is going to answer this question, will Trump win election and will Clinton be the next White House occupant? These are actually the same question. That was, I told you, there were 2016 election, the Clinton versus Trump elections. Weren't you born those days? Okay, so last election, Biden versus Trump. Will Biden be the next president of the United States? Will Trump lose the election, the presidential election, with the 2020 presidential election? Are these the same questions? Actually the same answer, right? But actually no words in common. Syntactically, these are just nothing, right? Any software will not actually equate that thing. This is actually called the paraphrase identification, right? Every time you cheat on your homework and you go to ChatGPT and you tell them, okay, here is Ahmad's answer, can you rephrase it? That's what you are asking. It's paraphrasing, okay? Paraphrasing that thing. That's what you do, right? Or this is called paraphrase. We worked on this thing called paraphrase detection, right? Well, that's actually when to became ChatGPT. So this paraphrase identification. The one thing. So what we were doing is this Twitter data set. You can tweet the whole thing, the same thing, in many different words, right? This is the whole art of this School of Social Sciences and School of Business or School of Law or all of them. Just teaching this thing. You ask them any simple question right? They will tell you, okay, इसमें दो बहुत ज़रूरी बातें हैं. That's how always is. You have to keep two things in mind, and then they will tell you the same thing twice, right? In slightly different words, right? Every type of thing you ask them, they will give you these 19 different answers with actually the same answer. But so the way we did it, so we got this Twitter data and we had this Microsoft data. There's a lot of Microsoft help desk data, and you know Quora, the question answer forum there, right? A lot of Quora gave us the data. So, and I said, oh, they said, okay, we have identified some of them is duplicates and some is not duplicates, not paraphrase, right? So it's called duplicate detection also. In database, this is called duplicate detection. They give you this kind of data and they said, okay, just try to learn a deep learning model to help us do the paraphrase identification. And the first thing I looked at the data and I said, let's see if the data is an equivalence relation, if the duplicate thing is an equivalence relation. We looked at it, and so there is a statement which is equal to a duplicate of statement A is a duplicate of statement B, right? And B is not a duplicate of A. Does it make any sense? It doesn't make any sense, right? If A is duplicate of B, then B should be equal to duplicate. These are the same sentence. This is the word duplicate, the word equality, the word paraphrase has this thing. And then if A is duplicate of B, you told me, and B is duplicate of C, Microsoft told me, and you are not concluding that A is not a duplicate of C, A is duplicate of C. That's a very logical conclusion, right? This transitivity, and also symmetry I told you, and also A is a duplicate of itself. It's the same sentence, even syntactically equal, right? So semantically, meaning wise, that should also be equal. Okay, so we got the data. We said, okay, let's see if it is something called transitive closure. We computed this transitive closure. We made it what's called an equivalence relation, right? And similarly, non-duplicate. If A is non-duplicate of B, then B should be non-duplicate of A, right? Or if A and B are equal and A is not duplicate of B, then A is not duplicate of C, then B is not duplicate of C, right? Do this kind of thing. Deep learning is extremely data hungry thing, right? It requires a huge amount of data. And you do this thing, you send it the data, huge amount of thing, and got very good results, actually the state of the art results at that time, and most probably still, that we can detect paraphrases, the same statement repeated twice or stated in different words. So these kind of things have a lot of application when you go further work in data science or machine learning. Look at this is a relation. This is what we used to call absolute value relation, right? Last time or the time before. Is this an equivalence relation? Is this a reflexive relation?
Yes.
Why? Because if a number A is equal to B or it is equal to the negative of B, then B should be either equal to B or then equal to the negative of B, A, right? B should be equal to A or the negative. So it is a reflexive relation, right? No, every number is equal to itself. So it is a reflexive thing, right? And symmetry I just told you, right? If A is the absolute value of B, if A is equal to the absolute value of B, then B is equal to the absolute value of A, right? Or the other thing, there is equality or equality to negative. Is it transitive? By the same thing, it is transitive, right? If A is either equal to B or equal to the negative of B, and B is either equal to C or equal to the negative of C, then A should be equal to C or equal to the negative of C, right? So it's transitive. This is a equivalence relation that we study. Here is another one that your compiler use it all the time. Actually, C compiler used it, and now people are using it with the same thing with different number. Let S be the set of strings, a set of strings made up of this alphanumeric and some special characters. Okay. Rn is a relation which just relates pairs of strings, and if a string is equal to another string, then they are related. Then that ordered pair is in the relation R. And if the strings are, if both the strings have length greater than or equal to n, right? The n is a parameter. If length of S and length of t are both greater than or equal to n, right, and the first n digits are the same, the first n characters are the same, then they are related. Okay, let's see this example. Is ABC and ABD in R4? Are they equal? ABC is equal to ABD? They are not equal, right? They are not equal, so they will not be in R4. If XYZ equal to XYZ, they are in R4, right? They are in R5 also, R6 also, because that doesn't matter. XYZ1, they are in R4, right? They are equal. String and string, are they in R4? They are equal, so they will be in R4, right? String and strike, are they in R4? They are not equal. They are not equal, but their length is bigger than 4, and now I am only responsible to check if the first 4 characters are equal. So STRI is the same as STRI, equal to the STRI in strike and string both. So they are related, they are both in R6.
So is this used in finding like related words?
No. This is nothing to do. This is a compiler thing. It's a very syntactic thing, no semantic meaning to this. It doesn't matter. Now I said the first n characters. No, the first n characters, C++ में भी counting तो counting होता है ना. The first 5 character means the first 5 characters. Their indices could be 0 to 4 or 1 to 5, that's a different thing. But the first 5 character means just the first one, the second one, the third one. You can call the first one a 0 index element. Okay. So the first n characters, if the first n characters are the same, then they are in Rn. Okay. How about this? Is ABC, ABD in R5? Yes. XYZ, because they are equal. It says if they are equal, then they are related. Okay. If they are not equal, then we may do something more. We need another check. Okay. That's why the string and strike are in R4, because they are not equal, but the first 4 characters are equal. Right. If they are equal, they are there in R for any Rn. I don't need to look at the length. ABC, ABD, are they in R5? They are not equal, and they are not equal. Let's do the other test. Is their length bigger than 5? No. So then out, right? Is compiler and compilation in R5? Yes. They are not equal. But let's do the first test, the second test. The second test says their length should be bigger than 5, and the first 5 characters must match. Their lengths are bigger than 5, the number of characters, and the first 5 COMPI and COMPI are both the same, right? String and string, are they in R6? They are equal. Equals are already there. String and strikes, are they in R6? They are not equal, but their first 6 characters, their length isn't bigger than 6, greater than or equal to 6. So the length is greater than or equal to 6. Are they bigger than 6? Yeah, they are greater than or equal to 6, right? But the first 6 characters are not the same. Yes.
तो यहाँ पर length of s and t जो है बार-बार n से comparison के बजाय एक दूसरे से comparison क्यों नहीं करते? Length of s equals length of t.
No, but this is, look at this compiler and compilation. What's the length of compiler?
7.
And what's the length of compilation? It's bigger, right? 8 or 10 or something, right? But they are both bigger than 7 or 6, whatever I wrote. Bigger than 6. And then I now need to do the other test, right? Okay, do you know identifier in CPP? Can you make a variable name FOR? Can you make a variable name while? WHILE? No, right? The identifiers are a set of strings that you are allowed to put this thing. Go home and hopefully it's the thing. In C language, R31 was the possible identifier. This exactly R31, other than this identifier. If you come up with a variable name which has 35 characters, right? And only the first 30, and another variable name which has 38 characters, right? And you do that thing, if the first 31 characters are the same, the C will be confusing the assignment. C will treat them as one variable. Okay? C will think that these two are, this is an equivalence relation. C would think these variable is the same. This is a generalized equality thing. Okay?
बहुत लंबा वेरिएबल होगा,
बहुत लंबा होगा in the first 31. So actually the first 31 characters is going to be the determining factor. Okay, I don't know about C++ or these new compilers, but C language, because I know the code of that, and it should be the same. Maybe it's R64 now, 63 now, something like that. Yes.
सर अगर आपने दो इंटीजर वेरिएबल्स बनाए,
Sorry, please.
सर if you make two integer variables, one has a length of 35, one has a length of 38.
The name of the variables have length of 37 and 38.
आपने एक को असाइन कर दिया 1, दूसरे को आपने कुछ नहीं असाइन किया, उनका कंपैरिजन करोगे तो फिर वो ट्रू
Now, if the first 31 characters are the same in the names, that's what it means, right? It's an equivalence relation. It's an equivalence relation. That's what we can prove. Identifier in C language used to be this R31 relation. Okay. Okay. This is what we'll do. Need a lot in number theory and cryptography. The mod of thing. A mod D. This mod is an operation. A mod D is an operation. It gives you the remainder when A is divided by D, right? So D has to be a non-negative integer, right? A non-zero, actually non-negative, non-negative. D has to be a positive integer and A is any integer, right? So when A is divided by D, what you get, I just defined an operation, right? Is this clear? So if A is equal to DQ plus R, this is called the division algorithm. We will see it some other time. Division algorithm. Any number A can be uniquely written as Q times D plus R for unique combination of Q and R. Right? If you divide a number A by some number D with the restrictions, there is a unique quotient and a unique remainder. Right? If you can't do this, that you divide two different numbers on D with by D, and you get the same quotient in remainder pair for both A and B where they are unequal, right?
कॉम्बिनेशन यूनिक होना जरूरी तो नहीं है ना,
Unique होना है ना. If you divide 17 by D, you will get a quotient and a remainder. If you divide 19 by D, you should get a different quotient and remainder. You can't get both the same, right? Have you ever divided two different numbers by the same divisor and got the same quotient and the same remainder? You will never. That's called the division algorithm, right? We'll prove that theorem when we do induction. Okay. So R is actually the remainder and Q is called the quotient. It's called A divided by B, right? The integer part of it. Typecasting, you know typecasting, right? So it typecasted so you do this thing. So essentially this is in C is this thing. If you do this, you will get, you will get A div D. Okay. Okay, that's not important. So I want to make the congruence classes. This is important. This is actually the whole number theory. The basis of number theory and cryptography is this number theoretic basic cryptography. X is congruent to Y mod K. This is a different mod K. Okay, this is not the operation. The operation is A mod K, B mod K, right? This is it's a relation. X is congruent to Y mod K if and only if the remainder when X is divided by K is equal to the remainder when Y is divided by K, Y mod K and X mod K. If they are equal, then we say X and Y are congruent mod K. Okay? There is nothing more to it. It's just the definition. I defined it. Yes, please. Well, that's a good point. So let's see, I have some examples here. No. So what is 15 more, what is 7 mod 4? What is 11 mod 4? 11 mod 4 is 2? Should be 3, right? What is 15 mod 4? 15 divided by 4, what do you get as a remainder? 3, right? So 7, 11 and 15 are all congruent. Mod 4, they are congruent. Okay? Are they equal? Is 7 equal to 11? But the remainder when divided by 4 is equal? No. Who said that? That is a different thing. 7 mod 4 is equal to 11 mod 4 because this is 3 and that 3 is equal to this 3. In this case, this whole sentence is equivalently is referred to as 7 is congruent to 11 mod 4. Okay? Congruent, I just defined it. I just used this word for you. There is no further concept to it. I gave it a name, right? So when two things, when divided by a number by k, has the same remainder, I will call these two things as congruent, right, to each other. Okay, so 7 is. So let's say R is a relation, which is the pairs of ordered pairs of AB, with if A and B are congruent mod 3, right? These are called congruence, things that are congruent, pairs that are congruent to each other mod 3. Okay, is this clear? Is this a reflexive relation? Is it a reflexive relation? Why not? Can there be a number whose remainder when divided by 3 is not equal to the same number when remainder of the same number when divided by 3? So 5 mod 3 is 2 and 5 mod 3 is 2. So 5 is related to 5, right? Every number is congruent to itself mod 3, mod any k. Does this make sense? I didn't say that this is not a set. So if look at this, you're reading too much into it. Don't read beyond the board other than the mod definition, the mod operator that was on previous slide. Okay, this congruence thing just came into being. I gave it a name. Whenever two numbers when divided by 3 have the same remainder, I will say these two numbers have the same, I will call these two numbers congruent, right? I just invented this name. Okay, I will say A is congruent to B if when I divided them by 3 or k or some number, and so if the remainder is equal, I will call them congruent. Just like I told you, 7 is congruent to 11 mod 4, right? 15 is congruent to 11 mod 4, right? Negative 1 is congruent to 11 mod 4. 3 is congruent to 7 mod 4. Okay? Yes? So now let's talk about mod 3. Is 1 congruent to 1 mod 3? Is 1 congruent to 1 mod 3? Just plug in 1 here and 1 here in mod k 3, right? So let's see. Is 1 divided by 3 the remainder? Is 1 mod 3? What is 1 mod 3? 1. What is 1 mod 3? So 1 mod 3 is equal to 1 mod 3. The definition is satisfied. I will say 1 is congruent to 1. Is 7 mod 3 equal to 7 mod 3? If x is 7 and y is 7, is x mod 3, 7 mod 3 equal to 7 mod 3? So 7 is congruent to 7, right? Is negative 18 mod 3 equal to negative 18 mod 3? Yes? So that's why negative 18 is congruent to negative 18 mod 3. Okay? Negative 18 is part of this R, right? So R is reflexive. Okay? For any integer is congruent to itself mod 3. So R is reflexive. Is R symmetric? Could it happen that the remainder of 7 when divided by 3 is equal to the remainder of 11 when divided by 3? Could it happen that the remainder of 11 mod 3 is not equal to the remainder of 7 mod 3? 7 mod 3, right? The remainder equality, this equality is symmetric. If x mod k is equal to y mod k, then y mod k is equal to 7 x mod k. That's why xy, if xy is there, then yx must also be there in R. Yes, please. Hoga, huh? Oh, sorry, I was the 7 and 11 came from mod 4. Yeah. 7 and 10 and 13 and 16 and 19 and anything plus 3 and minus 3 will be. Okay. So good, that was mod 4, sorry, wrong example. But if x is congruent to y, then y is congruent to x. Why? Because the definition says if the remainder is equal, then it's equal in this direction and that direction, right? And it's also transitive. It's also transitive, right? If a remainder of a and b are equal when divided by 3, and the remainder of b and c are equal when divided by 3, then the remainder of a and c are equal when divided by 3, right? That's again just the transitivity of equality of remainders, right? By the transitivity of equality of remainders, mod 3 divided by 3 is going to give us that congruence mod 3 is transitive. It's clear? If A is congruent to B and B is congruent to C, then A is congruent to C. Okay? So, this is an equivalence relation. So, I gave you this was our first example of an equivalence relation. I gave you the first example was equality. Equality is this thing. So, see, now congruence is not equal. It's not equal. Okay? But when we do cryptography, you will see for all practical purposes it is, we can treat them as equal. Okay, we can treat them as equal. They will behave exactly like equal things. Yeah.
Like for example, in the equivalence relation, we showed that if anything has these relations,
These properties,
then that is
any relation that has these three properties is called an equivalence relation. Yes.
this essentially is equivalent.
Yeah, this is an equivalence relation.
Equivalent
Yeah, you can call them equivalent, but I don't like words that I don't like. So this is R is an equivalence relation. Two things are equivalent. You want to say that two things are equivalent. Better we give them. These things are congruent here. In this case, congruent, right? It's clear. This is an equivalence relation between those two things. Okay. So let's say R is a relation which relates A to B if A divides B, right? If A is a factor of B, if B is a multiple of A, then I will say A, B are related, okay, on integers. Okay, if an integer divides another integer, I will say that integer, the divisor is related to its multiple. Is this clear? Yes? The relation clear? Is 1 6 in R?
Yes.
Is 2 6 in R?
Yes.
Is 2 7 in R? Is 3 6 in R? Is 3 7 in R? Is 4 6 in R? This 4 divides 6? No. So 4 6 is not in R. So you know what is this relation, right? Now let's see, is this relation reflexive? Let me say this relation is reflexive. Can you give me a non-technical description of this sentence? An English description of what does it mean? This R is reflexive. Yes. Every number is a divisor of itself. Every number divides itself, right? That's what we. Is it true that every number divides itself? No. I don't know. So this is generally positive integer. So you're right. 0 does not divide itself. This positive integer. Suppose we are talking about positive integer. Is it reflexive? Okay. Is it transitive? Is it symmetric? Is it transitive? If A divides B and B divides C, then does A divide C? Yes, it does. Is it symmetric? Why not? Is there a positive integer who divides another positive integer B and B doesn't in turn doesn't divide A? Yes. 1 divides 6 and 6 doesn't divide A. That's a good example and it tells us that this relation is not symmetric, right? Is this relation an equivalence relation, right? It's not an equivalence relation because it meets the reflexivity requirement and the transitivity requirement but not the symmetry. Okay. Here is another relation. Go home and do this. Okay. Very simple thing. I say R is a relation of set of strings of English letters such that AB is in R if and only if length of A is equal to length of B, right. So, if two things have equal length, I say they are related. Is this an equivalence relation? Is it reflexive? The length of every string is equal to the length of itself, right. So, that is why every string is related to itself. And similarly, if x has the same length as y, then y has the same length as x. So, if x, y are related, then y, x is also in R, right, and transitivity also, right. If x has the same length as y and y has the same length as z, then x has the same length as z, right. So, this is an equivalence relation. Which one? This one? So, this is just look at what, just read it. If two things are related, if their lengths are the same. So, that means everything is related to itself. Every string has the same length as itself, right? So it is reflexive. And if x is the same length as y, then y has the same length as x. That's why x, if xy is there, then yx is going to be there, right? And if x has the same length as y and y has the same length as z, then x has the same length as z, right? So if xy and yz are in R, then xz must also be in R, and that means this is a transitive relation. Both reflexive, reflexive, symmetric, and transitive means this R is an equivalence relation. Okay. Now, next thing, this is our last topic and the last concept. This is why I wanted to talk to bring a relation. There is something called an equivalence class, right? Equivalence classes are actually these unique concepts or unique topics or unique things in a data set. Okay. You have a ground set, you have an equivalence relation of this. Pick any element A, and all elements that are related to it is called the equivalence class of A. Now, because of this equality, right, so I am going to give you an example. R is called the equivalence class of A. This R is a subscript because we are referring to the fixed relation R. When that relation is clear from the context, we will just write like this A. This A is the equivalence class of A. Equivalence class is all element of the ground set to which A is related by the equivalence relation, right? Make sense? No? Okay. Let's just see this thing. Here is the relation. We saw it earlier, this absolute value relation. We saw that this was an equivalence relation. Okay. What is the equivalence class of 7? What are the things related to 7? Is 7 related to itself? Why? Yeah, because the relation R is an equivalence relation. It's a reflexive relation, right? What else is 7 related to? Negative 7, right? So 7 and negative 7 is the equivalence class of 7. What will be the equivalence class of negative 7? Exactly 7 and negative 7. Now, not just from this, not just from the fact that it's equal in absolute value, by the fact that this is an equivalence relation, right? If 7 is related to some number y, then and 7 is related to negative 7, and 7 is also related to some other number y, then this negative 7 should be related to that y. That's equivalence means, right? Reflexivity, symmetry, and transitivity mean this thing. Does it make sense? Yes? No? No, sir, what? Okay, good. It's okay. Let me just tell you this thing. This is an important thing. I'm saying if you have this thing, the equivalence class of A under some equivalence relation R, suppose this is the equivalence class of A. Is it correct? What should it be? It's an equivalence relation. So A must be related to itself, right? It's a reflexive relation. So this must be. So let's suppose this is the equivalence relation. Now I want to say that the equivalence relation of B, the equivalence class of B must be exactly the same set. Why? Why should A be here? Because A, B is there. These are the things related to A, so B should be related to A. Is it clear? Why is B here? Because R is an equivalence relation. Why is C here? Without blindly, why can I copy C from here? Transitivity and symmetry. Okay, first symmetry and then transitivity. AB is there, so BA should also be there. Right? BA is there now, and AC is there. So BA and AC means BC should also be there. That's why C should be there. Is it clear? So you take an element A and take everything that it is related to. Now these things, for all practical purposes, these things, the equivalence class of A is going to behave exactly the same as A. These are just equivalent stuff to A. okay, and this all follows from transitivity, symmetry and reflexivity, right. In this case, what's the equivalence class of 0? What is 0 related to in the absolute value relation? It's 0, okay. Did we talk about partition earlier? Okay. A partition of a set, please, this is last concept, I am going to give you an example. Partition of a set is a collection of subsets such that all pairs are disjoint and their total union is equal to the set, right. So, in plain English, it means that every element of this whole set A, the ground set A, should be included in exactly one subset, okay, in exactly one subset of this thing. So, earlier I told you, did we mention Lord Mountbatten today? Right. Okay. You ever heard of the partition of subcontinent, the Indo-Pak partition? Never heard this word? Is it a partition? Is it a partition? Look at the definition. What does it say? The answer is on the board. Is it a partition? What does a partition say? Take a bunch of, so let's say this whole thing is the British India. A1 is Pakistan, A2 is India and current Pakistan, and A3 is Bangladesh. Now I can ask, where does Lahore belong to? Lahore is in A1, right? Not in both. Can Lahore belong to A1 and A3 both? Right? That's what it says. Intersection of any two must be empty, disjoint, right? But where is Kashmir? In A1, A2 or A3? Is it in A1 or A2 or A3? Undefined, right? The second condition, there's nothing funny about it. Is the union of it, the union of Pakistan, Bangladesh and India doesn't make the British India, right? The subcontinent before 1947. Because Kashmir is in either or none or both or whatever, undefined, right? That thing is partition clear. Just literally partition things into certain parts, non-overlapping parts, not missing anything. You can't miss anything. That's what it says. You can't miss anything from S. You can't put anything in more than one. You can't bring anyone from outside, right? This is a partition. And this is the last theorem I want to tell you. Please listen. If I get an equivalence relation and I get the equivalence classes of an element, this must make a partition. Okay, it must make, each equivalence class will be apart. There will be no intersection because the transitivity will be violated, and there will be no, their whole union will be the whole ground set, right? So this is it. Please read this Mod 3 class we discussed. This is, I will start next time partial order, okay? Thank you.